Yeah, so I was told that I have to follow the time strictly. Okay, so 35 minutes plus 5. So my time starts now. Okay, so I'm going to talk about the MOT at blue narrow transition assisted by blue detuned cooling in rubidium. So first, I would like to introduce the elements which are being cooled, laser cooled internationally. Okay, so all these elements which are written with red font are being cooled. Okay, for different purposes. These two elements, rubidium and cesium, are extensively being used for quantum computation. Okay. However, there has been recent effort. Okay, at IIT Guwahati, at my place, we are cooling rubidium and ytterbium, okay, for quantum computation. And of course, recent effort is there for the quantum computation using strontium and ytterbium. Okay. So after introducing the element which are being cooled, let me introduce the group who is doing laser cooling in my lab. So I have 6 PhD students, and here is my lab. Okay, so this is basically set up for ytterbium. Okay, and this is the G-man slower you can see here, and this is I'm having very small setup for rubidium. Okay, but here I'm going to talk about cooling of rubidium. And first, let me tell you that how did I start cooling rubidium. First, we wanted to target the quantum computation using rubidium atom. And for quantum computation, Rydberg excitation is important thing. Okay. So in rubidium, there are 2 ways to do the Rydberg excitation. One is 780, and then another is 480 nanometer transition. And another possibility is, another possibility is 420 nanometer laser here, and then 1013 nanometer. And for the coherent excitation, it's important to have narrow line width of the intermediate state. If line width of the intermediate state is broad, it gives incoherence. And that was the motivation for us to do this. However, we have procured this 420 nanometer laser diode, and we are building this 1013 nanometer laser ourselves. And it is taking time. So in between, we thought that we have to do the laser cooling using this transition. Anyways, we have to do spectroscopy of 420 and so on. So we thought of doing this laser cooling. And why did we use this laser cooling of 420? Because it is having narrow transition, and then we expect that it can give lower Doppler temperature. So here is our energy level, relevant energy level for rubidium. Okay. And what we are targeting is the transition from here, 5s½ to 6p3½. The total line width of this excited state is 1.35, 1.2 megahertz. And it is having very complex decay structure. Okay, it's open transition, and out of 1.35, only direct decay is 320 kilohertz only. So we have very bad branching ratio. Okay, and then if it goes to this state, we have to repump, and we were not sure that this cooling will work very well in rubidium. Okay, because anyways we are repumping using IR, Okay, if we had two 420 nanometer lasers, of course, we can say that cooling will be more efficient, but we had only one 420 nanometer laser, and then we are repumping with IR. So we were not sure that using this IR repumper will really reduce the Doppler temperature. But we tried it, okay? So here is the scheme. 780 nanometer is the MOT, okay? And then initially we make the IR MOT and with 780 repumper. And then we transfer this MOT to 420 nanometer MOT, okay? Why do we need to do the step? And the answer will be given here in this slide. We can't directly load the blue MOT because of these parameters. So these parameters are very important for laser cooling. So we are having two transition, red transition and blue transition, we are comparing. The important parameter is single photon recoil, okay? And then, so what is meaning of single photon recoil is if one photon strikes, how much velocity kick it is going to get. So in Rubidia, with 420 nanometer transition, it is higher than this, okay? So it is interesting who are working in the gravitometry, because this is based upon this, the sensitivity in gravitometry depends upon the single photon kick. So you expect, if you are using this 420 nanometer laser, you expect to have better sensitivity for G. However, the Doppler temperature for the Doppler temperature for blue transition is 5 times lower, but the capture velocity is very small, right? So this is the reason why we had to do first red MOT and then transfer to the blue MOT. Now, if you want to do the blue transition, any laser cooling, we have to do the spectroscopy, okay? And spectroscopy is the important part. There are different ways to do the spectroscopy, okay? And one is the simply do the direct excitation. Since this transition is weak, it's not easy to get the spectrum. And also you should have blue photo detector. In our case, we didn't have any blue photo detector. The blue spectroscopy has been done directly. And one of the, for this paper, one of the author is here and he has done this direct excitation. But what we did double spectroscopy. And what is the idea is, since we don't have blue photo detector, we will detect 780 nanometer absorption in the presence of 420 nanometer control laser. So then we don't need photo detector which is sensitive to blue. Okay. And we did some spectroscopy and did some hyperfine measurement and so on. But there is issue. Okay, the issue is we are getting very high line width. Okay, it's the line width of that blue spectrum is around 30 to 35 megahertz. However, the line width we expect to be 7 or 8 megahertz natural line width. And this was the reason, because the Doppler shift for 780 and 420 is very large. Okay, so there is going to be a Doppler mismatch which broadens the line width. Okay, then we cannot stop. Then we said that let's do something else. What we can do is we can put, in order to reduce this, we can put one more control laser here, and we can put two counter-propagating 420. Okay, so in that spectrum of the blue, we get narrow dip. And so this is the spectrum we got. This is the green color is with this scheme. And the line width, okay, we got around 10 megahertz. So that is the idea. And then using this method, we continued to the MOT. Okay. So here is the scheme. We first make the MOT, we loaded this, and then we transfer the MOT to blue. So only we switch off this MOT laser, the repumper laser is on. How much time do I have here? Okay, 24 minutes. Okay, so 24 more minutes. Okay, fine. So, so this is our scheme. We do co-propagation of this and so on. And we had dual wave plate, okay? And then dual wave plate, we were not sure that it will work for both, even the company said that it is going to be lambda/4 for 780 and 420. But sometimes they provide lambda/4 for one and 3 lambda/4 for other. So it will produce opposite polarization. So we have to be sure about that. And how did we become sure about that? That in 3 arms, okay, so in 2 arms, we put 780 nanometer, and in 1 arm, we put 420 nanometer, and then MOT was coming. So we were sure that this lambda/4 was very good, and it is working for both. So this is our MOT setup, okay, and then glass chamber is here, okay. And what did we do? First, we load the 780 nanometer laser, which is, you can see from here, 780 MOT is visible. The typical loading time was 1.6, and maximum number of atoms was typically 10 to the power 8 atoms. And then after loading to the red MOT, we simply we remove the red MOT beam, and then we had this blue MOT. Initially, we detected using the photo detector that if you put some, if blue beam is there, you see the blue, if you see the fluorescence immediately coming. If a blue MOT beam is not there, you see again loading, okay? We were holding like 100 milliseconds. Okay, so this we did all these measurements because we didn't have camera also at that time. So once we got the camera, we started doing proper measurement. And here is our figure of the blue MOT. This is blue MOT, and this is red MOT after time of flight of 1 millisecond. So it looks really dense and cold. Okay, and then this is all these parameters. We were wiring the blue MOT laser detuning to transfer the number of atoms, and this is the curve. So optimum transfer was around 4 megahertz, okay? And we were wiring the blue MOT laser power, and then we got saturation. So I think we have enough blue power to transfer the number of atoms, all the atoms. And repumper power required was only up to 10 milliwatt, okay? This is another important parameter, that how these MOT are shrinking in the blue MOT once we transfer. So this is the radius of the blue MOT with time. So 15 or 20 milliseconds was good enough to settle the blue MOT radius in the blue MOT, okay? Okay. So one of the important point is, whenever I talk about this blue MOT in the presence of repumper, people immediately ask question, what about the ionization? Because when you are signing here, the laser, you are not only driving this transition, but you are also driving this transition, which is going to ionize. that was the one of the question. But we noticed that if we keep the detuning to around 7 or 4 megahertz, so what did we do? We make the red mode and we kept the blue beam on, and we saw that change in the number of atoms in red mode, and we saw that the number has reduced by 10%, which is the error bar of the number of atoms works. So it was okay. Then we further did one thing, that let's measure the lifetime of the blue mode by varying the blue mode power, because if there is going to be ionization, you are going to expect that the lifetime will decrease. So we varied up to 15, but and then we saw after 15 there is some decrease of the lifetime, but beyond that we couldn't go because we didn't have enough power. So this is the experiment. By that time we got the after that we got the photo detector, and then we did the blue spectroscopy, and here is our spectrum. The typical line width for this blue spectrum is coming to be 3 to 4 megahertz. And of course, it depends upon the temperature of the cell, which is the line width is increasing with increase of the temperature. And we also varied the temperature of the rubidium cell. And then for optimum signal, we had 90 degree. 90 degree was good to get this saturated absorption signal. Okay. Okay, this is probe transmission, I will say. Yeah. Yes, yes. Because of the collisional effect. And, and then also you see here the amplitude of this saturated absorption signal also goes down after 90 degree. Okay, so that's the idea. Now we have this blue photo detector, so we can play with detuning of the repumper and so on. Previously, it was very difficult for us to vary the detuning of repumper because on the repumper, blue laser was locked and so on. So it was very complicated. So now we have separate blue laser locked. So we can vary the detuning of the repumper. And as I told you that this transition is open transition. We have a lot of leak to the other hyperfine levels, and which we are exciting again by repumper. So before I go ahead, I want to introduce cooling, okay, using that is called blue detuning cooling, okay, and blue detuning cooling works for type 2 transition. So let me introduce what is type 1 and type 2 transition. Type 1 transition is if excited state hyperfine number, this Fe value is less than Fg, then it is called, sorry, if Fe is greater than Fg, it is called type 1 transition. Okay, so for example, type 1 transition is Fg is equal to 1 to 2, which we are using for repumper. If excited state is smaller than this is called type 2 transition. Less or equal, then it is called type 2 transition. And if we have repumper at 1 to 1, then it will be type 2 transition. It's well known that oh, that's good. Yeah, it has to be greater. Sorry, it's just copy paste issue. Okay, yeah. So it has to be greater, and then if it is equal, then it is equal or less, then it is. And then sub-Doppler cooling has been done, and one of the author is here. So all the difficult question I'm going to direct to him to answer, if I'm going to have. So here some blue detuning cooling has been done. So what it works, how does it work? Sub-Doppler cooling. What I'm saying, sub-Doppler cooling. Sub-Doppler cooling works for type 1 transition with red detuning. For type 2 transition, sub-Doppler cooling works with blue detuning. That's the take-home message. Okay, and then there are explanations here based on the light shift, and the reason behind that is, the reason behind that is, in type 1 transition, we have no dark state. Okay. In type 2 transition, we have dark state, and that is the root cause for blue MOT detuning, sub-Doppler cooling, which works with blue detuning because of this dark state. And this is very well known, red detuning sub-Doppler cooling, which is very well explained by this paper. And this is one of the important work for which Cohen-Tanauji got Nobel Prize. Yeah, that's very good question. People say that, okay, so, okay, I want to add one more thing. So sub-Doppler cooling at type 1 transition is said to be very fragile with the magnetic field. If you are having a stray magnetic field, the sub-Doppler cooling at type 1 transition goes away. Okay. However, it is said that type 2 transition with blue detuning can also survive. However, we are noticing here is sub-Doppler cooling transition at type 1 and type 2, both are surviving in MOT itself. That's the important point here I want to say. I hope it is clear. Sub-Doppler cooling, which is called optical molasses, which is explained by this paper, says that stray magnetic field will kill the sub-Doppler cooling. But we are noticing very well good sub-Doppler cooling even in the MOT, means in the presence of magnetic field. No, it considers both. So it considers sigma plus and sigma minus, and then they say that this polarization direction will rotate in space. Okay, it has both. Cis-Fus cooling is same. Cis-Fus cooling, polarization gradient cooling is same. Okay. However, recently this group, okay, from Tarbut group, they have said that sub-Doppler cooling works very well in MOT itself. Okay, previously it was said that it will not work, but they claim that it is going to work at type 2 transition. And they got blue detuned blue MOT. No, sorry, blue detuned red MOT. Okay. So what did we try after this? So conclusion is, it is known that blue detuned sub-Doppler cooling does not work for type 1 transition, that is 1 to 2, it is well known. And also it is very, very fragile to stray magnetic field. However, we tried here. We have blue MOT here, and then here we have repumper, which is driving this transition 1 to 2, and we are putting here blue. And we saw that the temperature is going down. And here is the plot for the temperature versus detuning. So if we are detuned like 20 megahertz, we are getting the temperature around 140 microkelvin. Okay. There is another group which has tried this blue detuning, blue MOT in NASA group, and they got similar temperature, but they are at resonance. So what we tried, we detuned, and when we are going to the blue MOT side, blue detuning side, our temperature is decreasing. F is equal to 1 to 2. I'm talking about repumper of this. Repumper detuning of this. Yeah. So you see that temperature is decreasing. Why? Because see, this is open transition. Lot of atoms are going here. This is repump. This is my primary laser, blue MOT laser. I'm plotting this detuning, right? Type 1 again. And type 1 again, it is said that blue detuning will not work. But that is only for the no, see, so here, this is repumping, but it is also cooling. That's what I'm saying. This is open transition. Lot of atoms are here. Okay, so it is basically helping us to reduce the temperature. By the way, we also tried with red MOT itself with blue detuning repumper, and of course it didn't work. With this blue MOT, it is working very well. Then we said that let's go, and of course the number of atoms after 20 megahertz is decreasing. So for us, the optimum parameter is around 20 megahertz. Yeah, so here is the answer. The answer is we are varying the intensity, power. And if we increase the power, the temperature is going down. This is also another counterintuitive. Okay. So we increase. So typically for red MOT, the repumper we keep around 10 milliwatt. But for blue, we are increasing and we are seeing that temperature is decreasing. So 28 milliwatt is the parameter. 266 megahertz. Okay. Then we said that let's go for this repumping. So we changed the repumping scheme inspired by this blue detuning cooling because we are having dark state. And we are having this temperature. So we are, of course, getting lower temperature even. There we were stuck with 70 microkelvin. Here we got like 40 microkelvin. And again, here is the power versus temperature. And you are thinking that it is, again, we can get, but we don't have enough power. But we took more data here to see whether it is saturating or not. And it's kind of saturating. Okay. Okay. So what is the take-home message? That blue detuned cooling is working for both type 1 and type 2. Okay? That is our conclusion. Okay. Now, inspired by this, we wanted to do blue detuned MOT at blue transition. That's what we wanted to try. And we know that for the red MOT, this is our MOT scheme. But if you want to do the blue MOT, if you want to do the blue detuned MOT, you have to change the direction of the polarization. Okay. So here it is sigma minus and sigma plus. If you want to make blue detuned MOT, you have to do here sigma plus and sigma minus. So here, what are we putting? One is making the red detuned blue MOT. And then we have another laser, okay, not another laser, another beam, which is exciting 2 to 2, which is type 2 transition with opposite polarization. And what we notice that, yes, it is working. By the way, 2 to 3, type 1 didn't work for lowering the temperature, but type 2 is working. So the number of atoms, of course, decreased, but temperature we got like 25 microkelvin. Okay, even further lower we got. And the optimum blue detuning for the blue detuned blue transition mode, we had plus 4 megahertz. And the typical power is 6 megahertz. We cannot go more than 6 milliwatt. We don't have enough power. So, okay, so this is what I can conclude here, that we are seeing the effect of the cooling even at type 1 transition with blue detuning. So this is our, I don't want to go for the continuous loading to blue mode. It will take another 5-10 minutes, which I don't have. So what is our goals? It's fine, but we are also setting up the array experiment. And we have created the array of the beam using very low power, 100 milliwatt, 805 nanometer. And then we have created this array. This is going to be our experimental setup for the quantum computation. And, and here we have created array. More intense array is only 1, 2, 3, 4, 5, 5 cross 5. So that is our plan. And we are trying to detect the atoms in these arrays. However, we have very primitive camera, which is not sensitive enough, but we are just trying and see. So thank you very much for the attention. I'm open for the question.
Thank you, Kanhaiya. You finished earlier.
Yeah, I was so afraid because of, you will simply.
Very nice, Kanhaiya. So I just have one question. So do you see in the time of flight images what you use for temperature measurement? Bimodal kind of profile or one single profile?
Single.
So there is, so you are claiming that this cooling is going on in the entire cloud rather than,
yes.
Because usually when you have blue MOT and red MOT, then, you know, when you start to take the time of flight, you see that there are some wing atoms, and so that is not there.
That is not there. And I also want to add comment, this blue detune, what blue detune at IR MOT by Tarbot group, they use 6 beams. So the intensity imbalance is very important. Otherwise this beam, the MOT becomes very weird. I mean, and so they had to take care of a lot of things. However, our blue MOT, so many blue and red is coming, I'm getting confused. It's very, very nice. The cloud shape and all, it's very good. And we don't have to worry about this intensity imbalance too much, because this blue MOT is taking care of this, because this is cooling, Doppler cooling, and this is doing sub-Doppler business. So it's the MOT shape and this thing is very, very good. Okay.
Yeah. Yeah, so really nice, Kanhaiya, the things. But this type 2 seems very similar to like this Bill Phillips, this gray molasses, right? Like
gray molasses. But gray molasses is again in the absence of magnetic field. In the absence of.
No, it's basically the polarization gradient between the dark and the bright states, right? So yes, but your type 1. So when we do PGC, we have found also that, like, you know, like kind of like coming more, like increasing the detuning more. Somehow with the lower state, maybe some sort of a gray molasses is still going on there, some sort of a dark state. Would you, I didn't understand the explanation for your type 1, because, you know, like.
Yeah, so type 1 explanation, honestly.
So is it like the lower level, the excited state is actually making it effectively in your definition, this type 2, and that you have some dark state, and which is.
Type 2 has dark state. Type 1 doesn't have dark state.
No, but I'm saying that effectively the lower F equals 1 may be actually creating a dark state, and that's why you're saying it. Like for type 1 also, I'm saying with that's the physics. Yes. So in your timing, you're shutting off the coils, no? So but you're not zeroing the field. Is that the problem?
We are shutting off the coil, and It's fine. I mean, we have.
So you have effectively zero magnetic. How do you know it's not PGC going on? Like usual polarization gradient pulling. With your field is not zeroed properly. Is that the?
No, field is 0, but
So then why type 1 is not the usual PGC explanation? Like, is, right? If you're canceling the field very well, then.
yeah, so basically we have done this experiment with magnetic field on and off. It doesn't make any difference.
Oh, I see. Okay.
Yeah.
Okay. Yeah.
Doesn't make any difference.
So you had mentioned about the issue about the line width of the intermediate state for the Rydberg excitation.
Mm.
So you could actually get around this problem by making a very large detuning from the intermediate state, like a few hundred megahertz. Then you can actually do, get rid of the dissipation from the intermediate state and, make an sort of adiabatic elimination and make it effectively a two-level system.
Yeah, so there are two things. If you want to have very high Rabi 2-photon transition, okay? So if you are decreasing too much, your 2-photon Rabi frequency is also going to decrease, okay? So I will show you the calculation and convince you that this narrow intermediate state line width matters, okay? And it is going to add incoherence. Okay, you can detune, but your 2-photon Rabi. So if you want to maintain same 2-photon Rabi frequency, okay, this intermediate state having lower line width is going to win.
Congratulations, very interesting work. You had made a statement that this blue detune mode will help in measurement of gravity.
Not MOT, but if you are doing this Raman.
Okay, so in Raman transition,
Raman
because
transition
of
blue,
smaller wavelength.
Smaller wavelength,
Okay.
so kick is going to be higher.
Okay, okay.
Yeah.
Thank you.
Just trying to understand. So is the conclusion that what is happening is not mainly subdoppler cooling, but dark state cooling?
Yes.
That's a conclusion, right? Because the temperature keeps going down. You also showed 20 microkelvin and all that.
Yes.
So that seems to suggest that most of the cooling is done by pushing the atoms to some dark state.
Dark state, yes. Yes. By the way, I mean, there is paper by Cohen-Panauji where he explains the blue detuned cooling only in two-level system. It's also possible to do blue detuned cooling only in two-level system. Okay, I don't have time, but I can explain how it works.
No other questions, it seems. I have one. You had this last image you showed, the array. How are you creating the array?
So here we are having MLA.
What?
MLA, no, it's not politician, it's micro lens array, okay? Yeah. Yeah, politician will not, okay, sorry. It's not recorded, right?
I mean, high power.
Yeah.